We're nonsense. You will remember when we proved this before, right? We proved it before. We spent like about 10, 20 minutes last time on that thing. I had to pull out a k to the k, right? I didn't do that yesterday in either section, and no one called me on it. But it was nonsense. You have to pull out the k to the k. If you look at section 11.4, are you ready? If you look at section 11.4, the argument in the book is legitimate and easy to understand and easy to follow. And so I would urge you to study, where was it? Page, yes, 551, part 4 of section 11.4. The proof is about 2 or 3 lines, but those 2 or 3 lines are important. So, you look at that, you try to understand it. You try to understand, well, if you want, you can try to understand what I did yesterday before why it was wrong. It was wrong because those things I claimed were less than 1. I had no such right to do so. And then I tricked myself. And you guys. 551, section 11.4, part 4. Proof there. Proof I gave you yesterday. Yes, no point anymore. Okay, any questions about the homework then? Like you just did it. Is there anything you'd like to see work? Yes?
I don't have it in front of me, so I don't remember exactly what number it was. It was in 11.4.
11.4.
And it was from negative infinity to infinity of sine of x squared.
That was 36, I think.
35. Yeah. Yeah, that one I can talk about. Sure.
I retried that.
So, the one you're thinking of is this one, the integral from minus 1 over n to 1 over n of the sine of x squared. All right. So here's basically the argument you can use. Minus 1 is less than or equal to sine of x squared is less than or equal to 1. Right? So by properties of the definite integral, this implies the integral from minus 1 over n, 1 over n of minus 1 x is less than or equal to the integral minus 1 over n, 1 over n sine of x squared dx is less than or equal to the integral from minus 1 over n, 1 over n of 1 dx. When I talked about this before in class, I presented it as an application of that. If you have a bounded function, the integrals are bounded by the integrals of the bounds. But you can also do it this way. Integrate the inequality. The definite integral, this is allowed by properties of definite integrals. But you know, these guys, you can just straight out calculate, right? This is just what? This is minus 2 over n. Do you see why that is? Generic principle of integration. If I integrate a constant, right, with respect to x over an integral from a to b, the answer is c times b minus a. It's one of those things that comes up enough. It's something I kind of have hardwired in my thinking. I think it's useful to know this. It's not hard to memorize, because it's really something that's easy to understand why that's true, right? Because that area is a constant function from a to b, so the length of the rectangle is b minus a, and the height of the rectangle is c, so c times b minus a is the area of the rectangle. So I just used that 2 times. One for the lower integral, one for the upper integral. And then what? What? Plus or minus 2 over n goes to 0, right? As n goes to infinity. Therefore, by squeeze theorem, it's not a capital T, or pi. Squeeze theorem, we have the integral from minus 1 over n to 1 over n sine of x squared dx goes to 0. Thank you for asking me about that problem. Makes me feel better. The ones they were asking me about in the earlier section were hard. I got stuck. Still not entirely assured about the validity. This whole string of yada 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 here. I don't know. There's something off. Other questions?
11.7, number 66.
11.7, number 56.
66.
66. Ah, yeah, I like this problem. This is a nice problem. Hey, if you don't mind, let me talk about this one so I can erase it. This was the Laplace transform problem, right? So you're supposed to find the domain of S for which this integral converges, basically, for given different choices of f of x. In particular, the problem we looked at was f of x equal to e to ax, right? So you feed e to the ax into the Laplace transform, that amounts to calculating this proper integral of the product of e to the minus sx times e to the ax. But by properties of the exponential, that's x times a minus s, right? But by definition of the improper integral, that's the limit as t goes to infinity of the integral from 0 to t and e to the x times a minus s dx, right? Well, I've erased that by something. That was minus whatever a minus s plus 1 over s minus a. That's how I like to write it. There we go. Now, what was going from here to here? It's just a basic integral, right? If you have e to the beta x dx, the integral is what? 1 over beta e to the beta x plus a constant, right? So I'm using this to go from here to here. And of course, fundamental theorem of calculus. Sorry. Does that make sense so far? Where did I put that? Grant Sisson, Brett Weaver, Don Roper, Marcus Gibbons, Jared. All right. I think we've established that they don't exist. All right. Brett. Brett's not in here, but Brett still exists. All right, anyway, that's Brett. Trying to get some stuff back to you guys. Where was it? I had a particular, I had yours, Peter. Where did I put it now? Oh, here it is. So you guys good with me on the integration? Other people? Zachary Baybridge? And Zach Coleman? All right, so getting back here. So this was just integration, right? And then you have this. And I just cleaned it up. It's the same as here, right? The thing is, this diverges if the multiplier of t is positive. Right? If the multiplier of t is positive, then that's it. I mean, what does it do? It goes to what? Infinity, right? And if it's 0, that's just 0, I suppose, right? I mean, if a is equal to s, it's 0, which is fine, right? But it's funny. Well, a equals to s is problematic for other reasons, right? If a is equal to s, I can't divide by a minus s. That would be bad. So I think you need a separate argument. In the case s is equal to a, in the case s is equal to a, this is the integral of 1 from 0 to infinity. That clearly diverges, right? That's the limit as t goes to infinity of t, which is infinity, so it diverges. Separate argument. You can't have s equal to a. Hey, nobody called me about this earlier. You know, yeah.
The 1 over, when you find the limit of both of those, when you separate them, isn't 1 over a minus s, isn't that a constant?
Yeah,
So therefore, you only be finding a limit to, which is e to the t times a minus s.
right, I just, the thing is, mostly I have to analyze this is just a constant which rides along, right? I agree, I mean, so if the multiplier of t is negative, then this piece goes to 0, and you're just left with that constant term. So that's why the Laplace transform is 1 over s minus a in the case that a minus s is less than 0, but that's more nice to write as s greater than a. So the question was two things, was find the Laplace transform and find the domain of s, which is relevant. Okay? So by the way, a lot of you guys are aspiring electrical engineers, right? This is an important example, the Laplace transform. Usually we don't use x, we use t for time, and s is called the frequency domain. It is what it sounds like. T has the physical meaning of time, s has the physical meaning of frequency. And this is a useful way of solving circuit problems that involve discontinuities. It used to be that there was this thing called a switch on a wall that I could have gone and switched off and on to illustrate switching, but not possible. Domino was too smart. But anyway, Laplace transform is a really neat technique because it allows you to solve problems that have different cases in one file swooping calculation. Like if you think about how we do things right now, if you have a piecewise defined function, right, what do you have to do? You have to solve, you have to break and basically analyze the different pieces one at a time. And if it's like a differential equation or something, you have to then glue the solutions together for the different domains using continuity at like the edges or something if that's physically appropriate. That's really a pain. Well, Laplace transform is this tool that just kind of makes all of those different cases meld together into one single case in the frequency domain. You solve it there, transform back, and you get a solution. This technique that I'm describing, called the method of Laplace transforms, of course, is covered in the differential equations course. Any questions about this? Now, the one you asked me about involves a piecewise defined function, but that one's a little simpler because one piece is 0, so nothing really happens for the 0 piece, right? I better erase this before you guys ask me about it. Yeah.
Are we expected to know how to do Laplace
Yes.
transformation?
Oh, no.
Okay.
I'm sorry, whenever somebody starts asking what's on the test, I just like, it's just knee-jerk reaction, I say yes.
That was more just difficult.
No, that is a homework problem, which we have assigned for prep. There are certain terms in the homework I would like you to know. Asymptotic, right? The definition of asymptotic functions. I would like to know what a probability distribution is, right? And there's a few other things. I'll look through the homework and try to make a list of these things. Well, the Laplace transform, we'll let you learn the definition of that in the differential equations course, okay? Yeah. If I was to ask a question about that, I would include the definition of Laplace transform in the question, much as the book does. You're supposed to, what is it, find a k, or what was the question? This is number 66, right? Like k greater than 0, show that this is a probability density function of, okay. So you have f of x defined in cases. You've got 0 if x is less than or equal to 0, right? And you've got k e to the minus kx, I guess less than 0, if x is greater than or equal to 0. That's the definition of the function. We're supposed to show it's a probability distribution function, right? So what does that mean? What do we need to show? The integral from minus infinity to infinity, right, of f of x dx is equal to 1, right? Sum of probabilities must be 1. Okay, so here we have the integral from minus infinity to infinity of f of x dx, right? But that's equal to the integral from minus infinity to 0 of f of x dx, right? Plus the integral from 0 to infinity of f of x dx. this is by definition 0. If you didn't pay attention to this, right, and you just tried to integrate k e to the minus kx from minus infinity to infinity, you found that it diverged, correctly so. Okay? Okay, so this is what? This is really the limit as t goes to infinity of the integral from 0 to t, right? F of x for x positive is what? It's, or not negative, I should say, it's k, e to the minus kx, right? And that is what? We can integrate that. I mean, that's what? That's just minus e to the minus kx, right? If you doubt me, differentiate my alleged antiderivative. What do you get? Yeah.
Should get 1.
Mm-hmm.
No, 0, I'm sorry. Get that.
So differentiating gives me e to the minus kx times minus k, but that minus cancels the minuses there, giving me plus k e to the minus kx. You can get this antiderivative by doing a u equals k minus x substitution. But at this point in your life, you really shouldn't have to write that out. What I'm suggesting to you is that this integration, by now, you should have done it enough that you kind of do this without even writing it down, the details, yeah? I don't require you to write the details of that integration, so you don't have to, you know what? Anyway, so that's what's behind the scenes here, beta equals to minus k, right? All right, so then what? This is the limit as t goes to infinity of minus e to the minus kt plus e to the 0. Because the minus minus gives me plus in the calculation of the fundamental theorem calculus 1, 2. Of course, this doesn't. This goes to 0 because what? We had k was greater than 0, right? So minus k is less than 0. We have t multiplied by a negative number, exponentiated. That goes to 0 as t goes to infinity. And we're just left with 1. So yay, it's a probability distribution function. How can I make this a more interesting test question? Make it what?
Not make the x less than 0 equal 0.
Not make the x less than 0 equals 0? I guess I could do that. I was thinking something like, make it all mysterious and be like, A, and then like, find value of A to make f of x probability distribution, yeah? That's more fun for me to grade. If I tell you guys to show me something is true, it's much harder to judge whether you know what you're doing. I leave a little mystery. You see, you tell me A is anything but K, I know you don't know what you're doing. Easier for me to grade. Sorry, I get excited about things that are easier to grade. You don't have to. It's the same question though, right? Remember when we worked out, we had like K over dx over 1 plus x squared, right? And we integrated that from minus infinity to infinity, and we found the value of K, which made it a probability distribution. So it's almost the same question. You just end up with an equation A equals to something, and you force it to get A equals to K. But anyway, I digress. Other questions? Yep.
Are we gonna have to know any like proofs for the
Yeah.
test?
Yes.
Which ones?
I will make an announcement. I mean, certainly ones that were in the homework are fair game. I'm particularly thinking of the sum of the limits and the scalar multiple of a limit homeworks. Remember, you had if a sub n goes to L, b sub n goes to m, then a sub n plus b sub n goes to L plus m, and also alpha times a sub n goes to alpha times L. Those are certainly on the list of possibilities. Beyond that though, let me think about it. I'll make an announcement to be specific. Yes, sir?
Number 69 on 11.7.
Yeah, 69 on 11.7. Well, one direction of that I can prove. The other direction, I'm not sure what I'm doing yet. So, I mean, I have to think, I'm still thinking about that problem. I will say this, there's a theorem which is not too hard to prove, which is that if, right, the limit as x goes to infinity of f of x is equal to L. And here I'm saying for, f continuous on, let's say, 1 to infinity. All right, if the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of, f of n is equal to L. So here I'm contrasting, of course, continuous limit with a sequential limit. The question is an if and only if thing, right? So I think I can prove this without a lot of work, right? If I have, so how's that go? If you let epsilon be greater than 0, you can choose what? Let's say k. Maybe k is the wrong letter. Let me say m in the reals such that what? If x is greater than or equal to m, let's say, then the absolute value of f of x minus L is less than epsilon, right? That's the definition of an infinite limit. A continuous infinite limit means that you can, for each epsilon greater than 0, choose a positive, or positive, I suppose, m is greater than 0. I guess m doesn't have to be greater than 0, but I usually think of m as being greater than 0. I don't see it as m as entirely, whatever. Anyway, you can choose some number such that if you go beyond that number to the right on the number line, the distance between f of x and L is less than epsilon, right? This implication is forced. It has to happen if we're given the limit exists. That's what that means. Say the limit as x goes to infinity, f of x is equal to L. What is required then to show the sequential limit exists? See, all you gotta do is, so choose, I don't know, let's say k equal to the ceiling of m. So in other words, if I look at the number line, and here's m, right, and here's like integers, then this right here would be the ceiling of m. It's the next integer up the number line, right? So if I use that as my k, if n is greater than or equal to k, that implies that f of n minus L is less than epsilon. I have in fact the inequality for all real x. Beyond that point, in particular, it applies to integers. And so that is all that's needed to say what? Thus, f of n goes to L by definition of the sequential limit. It's turning this around that is subtle, because that problem has to do with only if, right? So I'm a little bit stuck on what conditions I need to go the other direction. I have a suspicion I need to use the bounded monotonic sequence theorem in the other direction, but I haven't wrapped my mind around it just yet. And you'd say, if you're looking at the problem right now, you might be going, what on earth are you talking about? Because that's not what the problem's about, right? What's the problem about? Areas, right? The problem asks you something like integral, what is it, 1 to x, f of t. How's it go? you're supposed to say something like the limit as n goes to infinity of the integral from 1 to n of f of x dx, right? Converges what? If and only if what? The,
Base of n is,
this is the ace of n,
oh,
I think. I'm not looking at the integral from 1 to infinity of f of x dx converges. Now, we're given some fine print too, right? Here, what is it? F of x is what? Positive, decreasing, right? What else?
Continuous.
Continuous, yeah. So, for me, the way I think about this is I look at another function, say g of x. How do I define g of x? G of x is the integral from 1 to x of f of, did I say x? Oh, fine, f of t dt. That's the area function of f, right? So we're really asking if the limit of the area function as x goes to infinity converges. Is that true if and only if the sequential limit of the area function converges? Are those equivalent, right? Well, certainly I can prove if the continuous limit of the area function exists, sure. Like I have no trouble going from this to here because I can look at g of x. What's g prime of x? It's f of x. So g is differentiable. So it's certainly continuous, right? If the limit as x goes to infinity of g of x is, L, then the sequential limit of g of n is also going to L. So that gives me the upward arrow, all right? But the downward arrow, I don't yet understand. But again, I haven't had enough time to work on it yet. So these are the things I'm thinking about for this problem. Think about area function, basically. Anybody have a totally different proof? I think this is the last problem in the homework, right?
Yeah.
Anyway, I probably shouldn't even talk about this in class because there are other more important problems to talk about. Other questions? Again, I think that the other arrow is subtle. I will hopefully have a solution for you to look at in the homework when I post it. Yeah.
So with the problem there on the left, the fact that the limit goes to 1 constitutes that it's the probability function.
Right.
Why is that?
That's the definition of a probability distribution function. The area under the probability distribution function for a particular range of x illustrates the possibility that set x is exhibited in the system. So like, if you want the probability that for this system, that you go from, say, A to B, then you just integrate from A to B of e to the minus kx dx. Well, that depends on, I'm assuming here, of course, A, B, some subset of, 0 to infinity. Otherwise, I have to, the probability, for example, that x is between -3 and -2 is 0, because the probability distribution there is 0. There's no probabilities distributed there. But this, I would just, it would be that. It's just a definition. We explain it more in your what? For most of you guys, the what, engineering statistics course? Or for your math majors, math 211 or maybe 401, I don't know. Yeah, yes, sir?
On 11.6, number 25, did you have to multiply by the conjugate?
11.6, number 25. Oh yeah, that we talked about. That's the one where you have to multiply by conjugate. Yeah. So you multiply by like square root of x squared plus 2x. n square root plus x divided by the square root of x squared plus 2x plus x downstairs. And when you do that, it'll make a fraction. But I'll post a solution so you can look at that one, or hopefully do. Yeah.
Can we go over the proof on quiz 2, or I think actually quiz 3 maybe? I think most of us probably got that wrong, didn't know how to prove, like the limit of n as n goes to infinity, a sub n equals L.
You mean the statement of your definition?
Yes, it's the
Right,
definition of
specific,
low.
right, another specific definition. Those, I'm really getting hung up on those specific definitions, I've hardly ever heard of specific definition of something.
Well,
It's helpful to know how to find that, how to show that.
sure. A safe thing to do would be to simply memorize the blue text bubble on page 538, limit of a sequence. I will write that down. If for each epsilon greater than 0, comma, there exists a positive integer k, page 538 rather, positive integer k, such that if n is greater than or equal to k, then the x value base of n minus L is less than epsilon. And let's see here. There's a lot of ifs and thens going on here. Let me kind of use a color coding here. There's this big if at the start, all right? All this stuff happens, then a sub n goes to L. What's in pink is the condition that's needed to be met for the limit to exist. Important aspects of the theorem. Epsilon, you don't choose. Okay? You have to have epsilon greater than 0. It's an arbitrary epsilon. You don't get to pick it. Then there has to exist, a positive integer k, such that if n is greater than or equal to k, then, now, I also sometimes, here's my typical jibber-jabber for it. I say if for each epsilon greater than 0, there exists, k in the natural numbers such that n greater than or equal to k implies the s value of x of n minus L. Let me write out the word implies.
This is the same thing.
Less than epsilon. Then the limit as n goes to infinity base of n is equal to L. This is grammatically equivalent to what I've written in the pink. Yeah,
So this is saying that you give me an epsilon and I find a k.
yeah. I mean, that's how the proof works. If you want to verify the truth of this for a given sequence, I get your epsilon greater than 0, you have to show me how to pick a k to make it so. What other definitions should you really know in here? I mean, some simple things, right? Like a sequence is a function of what? Integers, right? Positive integers. What does it mean for a limit? You should understand what we meant by boundedness, right? What's an upper bound for a set? What's a lower bound for a set? What's the least upper bound? What's the greatest upper bound? What's the least upper bound axiom? What do we mean when we say the limit of a sequence is infinity? Can you define that carefully? Okay, these are other things you ought to be able to define. If I asked you to prove something like, say, the limit, and then goes to infinity of the natural log of n was equal to infinity, would you know what to do? show this, not just, I mean, usually we don't have to show it, we just go, well, I know what the natural log looks like, so that's clearly true, right? How would you prove it? Yeah.
Well, I want that to be 1 over n, correct? Oh, if you take the limit, I'm sorry.
No, no L'Hopital's rules allowed in this proof. I mean, I'm talking about a proof from base principles here. You have to do something like this. If for each m greater than 0, right, there exists k in the natural numbers such that n greater than or equal to k implies that the absolute value, well, yeah, the absolute value of the natural log, in this case, the natural log of n, I don't need absolute value here, if the natural log of n is greater than m, then that means that the natural log of n diverges to infinity. In other words, for each positive number, you have to be able to exhibit for me a positive integer such that everything in the sequence beyond that point is larger than m. You have to be able to do that for arbitrary m. If you can do that, you've shown the limit of the sequence is infinity. Yep.
So we couldn't just draw a graph?
No, not if I ask for a careful proof using inequalities. Now, if this is just part of some, like, if this is part of, there's going to be a question of the test, which is just like find this limit, find this limit, find this limit. If I use the word find, right, you are free to use intuition, put numbers in calculators, use graphs, whatever, right? If I say justify, then you need to do what? You need to use like algebraic arguments, L'Hopital's rule, squeeze theorem, stuff like that. If I say prove from the definition, it means prove from the definition. There's these 3 levels of minutia, right? The first one being the most free, the last one being the most demanding. I would typically only ask you to prove from the definition for the most simple of possible examples. This one, you're trying to do what? You want natural log of n greater than n, right? What n should you use? How about this? This means n is greater than e to the m, so that k equal to like the ceiling of e to the m. That should probably work. The next positive integer past e to the m. If you take n larger than that, right? N greater than or equal to k equal to the ceiling of e to the m, right? So by the way, this is greater than or equal to e to the m. But log is increasing, so we have the natural log of n is greater than or equal to the natural log of e to the m, which is m. So all you have to do is understand the definition and study the inequality you have to solve and kind of work backwards. Listen, I'm going to post a quiz for you guys. I'll post it on Blackboard or whatever. It won't be something you have to turn in. I'm just going to post a few like problems I might have put on the quiz today if I had actually had time to make a proper quiz. I didn't. Sadly, apparently I have to sleep. Annoying, right? But, I guess that's so annoying. You can sleep more. But, thank you guys, are nice. But, I will post a quiz, quote-unquote quiz, not an actual quiz, but a quiz that could have happened in the perfect world at that time to make the quiz for you guys. And I will also post a solution to that quiz. Essentially, this will serve as a pseudo-practice test in regard to that kind of question. Right? So I'll try to give you an example or 2 more. We did one before, I forget for what, was it for n squared or for, I can prove something goes to infinity using inequality arguments in here, but maybe just, yeah.
One quick question about the comparison test. When you pick your comparison, is there a trick or is it just intuition?
For me, the comparison test, what I always do is, oh, by the way, this is how to integrate that velocity problem in your homework. But it didn't ask me to do that, did it? It just said, here's the solution to work with it, didn't it? So, but you could do it by the integrating factor. So what I do, when I'm faced with comparison theorem problems, is I look at what I'm given, you know. Well, first of all, if I've got integral from, say, like 0 to infinity of f of x dx, what I a lot of times will do is go, okay, well, that's really integral from 0 to 1 of f of x dx, right? Plus the integral from 1 to infinity of f of x dx. The reason I do that is because then I can compare this to what? My standard grab bag of examples, which is this guy, right? We could call these the p integrals, right? So if p equals 1, it diverges. In fact, if p is less than or equal to 1, it diverges. If p is greater than 1, it converges. So those are kind of my go-to examples. I mean, that's the start of my thinking. And then, once I decide intuitively whether I think it converges or diverges by comparison to a p integral, then I have to come up with an inequality which supports my claim. So, yes, sir?
When you do the comparison, do you, when you split it up like that, do you compare both of the integrals to that one integral?
Well, this is just a number, right?
Right.
That's just a number. So the ultimate fate of this integral completely rests on what happens to this. If that piece converges, this converges. If this diverges, that diverges.
So we just need to know if it converges or diverges, no specific. If it converges, do we need to know a specific limit as well?
Oh, well, I can also ask about that. We had a bunch of homework problems where you actually have to calculate it directly. But if you're just asked to compare, I mean, an example I worked yesterday, right, was this, right? Integral of dx over x minus ln x, right? And we said that that was infinity by comparison to what? Equals to 1, right? And the reason that was valid is because we had this inequality, right? 1 over x was less than or equal to 1 over x minus ln x, right? For x greater than or equal to 1. So if the p equals 1 diverges, certainly something larger than it must also diverge. See? But no, I wouldn't actually ask you to calculate the value to which the integral converges, because I wouldn't want you to integrate 1 over x minus the log of x. That's kind of part of the point here, is comparison. The comparison test allows us to estimate integrals that we can't directly calculate. If we can think of some function that's similar to it, and related by inequality, then I can use what happens for that function to figure out something about the integral of a function I can't actually integrate. This, of course, is sneaky. Yes. But I think that the p integrals are a good starting point for that. Not an ending point, but a good starting point. Anyway, I'll at least have the solution to the 2 homework problems about those. And maybe if I have time, I'll try to work a few more of those in the homework, because I know you guys need more examples of that. Okay. Anyway, I guess it's time for your quiz. So, quiz 3.